Hello everyone, welcome back to the course on measurement and instrumentation, and today is the fourth lecture of 11th week. Today we are going to discuss about oscilloscopes. We are discussing our last module in the course and we are talking about data acquisition system. When I say oscilloscope, it means a test instrument which is used to visualize electrical signals of different nature in laboratory as well as in the industries. Okay. Oscilloscope displays the voltage of a signal as a function of time on a screen. Okay. So, you can see a basic waveform on the screen of an oscilloscope, okay, which has x-axis as time and voltage on your y-axis. Okay. This is just one way of representation of oscilloscope waveform. You may also have voltage on this y-axis as well as you may have another voltage on the x-axis. Okay. So, this is also possible. So, this is one mode, voltage versus time. We can say that this is say normal mode of operation of a oscilloscope. Okay. And we may also have a XY mode where I have voltage, one voltage in the x-axis and another voltage on the y-axis. By observing the waveform, we can analyze different properties of signals, like we can comment on the signal amplitude, we can comment on the frequency, on time period, we can find the rise time, fall time, we can also calculate the noise in the signal, any distortion in the signal and so on. Means that you can analyze your complete signal. Till now, whatever instrument we have seen, say ammeter or voltmeter, you had a particular data for particular instant. Okay, but this trail of data is not available there. Okay, here you have a trail of data for few time period, or you can also plot this voltage versus another voltage. So, you have kind of better opportunity to visualize the signal that is generated by different systems that we have studied till now. Okay. Instead of only measuring a value like was given by a voltmeter or ammeter, the oscilloscope shows you the entire waveform of the signal. Okay. There are different type of oscilloscopes, like you have analog storage oscilloscope or analog oscilloscopes, or you have digital storage oscilloscopes. Okay. Earlier this was only analog oscilloscopes where you have only analog signal, but in the modern scenario storage oscilloscope in analog is also possible. Okay. When I say analog oscilloscopes, this means mostly CRO, okay, cathode ray oscilloscope, and in this course we will mostly discuss about basic kind of CROs. Okay. Apart from this, we have mixed signal oscilloscopes as well that is available in the market, but for this course we will only discuss about these two in very brief. Okay. The CROs has a CRT display where it is based on cathode ray tube. We will see what is a cathode ray tube in some time. Okay. A CRO has continuous waveform like something like this that you can see over here. Okay. Real time signal display is possible based on whatever input you are giving, and it has limited storage capability, and that is why people has moved to DSOs. Okay. If you see this CRO and the output from this CRO, it looks like kind of XY plotter, but kind of very fast. Okay. Displaying an input signal versus another signal, or as I mentioned, versus time. Okay. The stylus of this plotter is not a physical stylus. Okay. It is a luminous spot which moves over the display area in response to an input voltage. Okay. The luminous spot is produced by a beam of electron which is striking a fluorescent screen. We will see in the CRT that there is a mechanism to generate a beam of electron which can be deflected by certain mean on a fluorescent screen, okay, which produces this kind of signals. The normal form of CRO uses horizontal input voltage, which is an internally generated RAM voltage. This is known as time base. We have seen that RAM voltages are the voltages. In case of ADC also we have seen that there is a slope and this voltage is keep on increasing. It may have a positive slope or negative slope, but based on that you have positive ramp and negative ramp. Okay. This horizontal voltage moves this luminous spot periodically in horizontal direction from left to right over the display area or this phosphor screen. Okay. The luminous spot thus traces the waveform of input voltage with respect to time. When the input voltage repeats itself at a faster pace, the trace on the screen appears stationary, otherwise it will look as a moving trace of signal. Okay. So, one thing is very clear that these CROs are based on voltage, or any kind of deflection in this beam of electron is directly proportional to the input voltage. Okay. However, when you want to generate signal for different physical quantities, okay, sometimes it is not possible, because ultimately what you need is a voltage form. Okay. So, however, there are steps to convert, there are equipments or devices to convert this say current or strain or acceleration or pressure or any other physical quantity into voltage with the help of various transducers. So, when you provide input to a oscilloscope, one thing is very clear, that the whatever be the previous stage, the output of the say previous stage, say this is the oscilloscope. Okay. So, the input of a oscilloscope should be a voltage waveform. Okay. It should be voltage. So, just before there should be a conversion from this transducer, say I am placing a transducer over here. Okay. This transducer should be able to convert any input form, maybe as I have mentioned, current or any physical parameters like change in capacitance, change in resistance because of any other physical parameters like strain or pressure or force, into a voltage waveform. Okay. So, just outside this or at the input of this oscilloscope, there should be a voltage signal. Okay. So, therefore, whatever kind of signal you have, the conversion from that to voltage is always possible with the help of these transducers. Okay, means that it is possible to present visual representations of a number of signals or a variety of dynamic phenomena on the CROs. Okay. The vertical input to the CRO is the voltage under investigation, and the vertical input voltage moves the luminous spot up and down in accordance with the instantaneous value of the voltage. We have already seen that there is a provision for sweeping from left to right, as well as, of course, when it has swept from left to right, it also has a capability for coming from right to left. But at the same time, you have independent kind of movement of this spot on this screen in the vertical direction. It means that you can place this spot ideally at any position on the phosphor screen. Okay. The CRO therefore provides a mean of visualizing time varying voltages, and it has become a universal tool in all kinds of electrical and electronic investigation. So, you can display anything from few microvolt to some volts. So, it can handle large amount of data. Okay. So, they are also used to investigate waveform, transient phenomena and other time varying quantities associated with the signal. Therefore, quantities can be anything from a very low frequency range of signals to as high as a radio frequency signal. Okay. A basic analog oscilloscope will have this many components. You have a probe, okay, a vertical amplifier, delay or delay line, trigger circuit, a time based generator, a horizontal amplifier. We have also seen that there is a vertical amplifier, and a CRT or a display to showcase the data that this probe has captured. Okay. Let us see what is the role of each of them in a oscilloscope. Okay. But before we actually see the components, let us try to understand the basic working principle, so that it will be very easy for you to connect with these components. Okay. The oscilloscope works by deflecting electron beam based on the input signal and a time based signal, as we have discussed earlier. Okay. Now, input signal enters through this probe. Okay. This signal is amplified or by this vertical amplifier. Okay. It passes through this delay line. All right. And this trigger circuit synchronizes the signal. Okay. This time based generator produces a sawtooth waveform. We will see what is the use of this sawtooth waveform. Okay. And this sawtooth waveform actually drives this horizontal amplifier. Okay. So, vertical signals control the vertical deflection and horizontal amplifier controls the horizontal sweep of time or other voltage, we will see. Okay. And accordingly, the data is displayed on the CRT. Okay. So, in the measurement, vertical deflection means the signal amplitude. So, this means the signal amplitude, and horizontal display here, if it is working in a normal mode, display the time. Okay. So, now let us understand the role of all these components in very brief. Okay. This is the probe that is connected at the forefront of this oscilloscope, and the probe connects the oscilloscope to the circuit which is under test. Okay. So, its function is to transfer signal from circuit to the oscilloscope. Okay. It also helps minimizing the loading effect on the circuit. Okay, and maintains the signal integrity. Okay. There are different type of probes depending on the oscilloscopes as well. We have passive probes, active probes and differential probes. Okay. Then the second stage of this oscilloscope is a vertical amplifier, and its role is to amplify the input signal before it is displayed. Okay. So, it actually amplify a weak signal, adjust the vertical scaling and control the volts per division. Means that it has direct role in the control of the sensitivity. In fact, the vertical amplifier is the principal factor in determining the sensitivity and bandwidth of any oscilloscope. Okay. In general, greater sensitivity is obtained at an expense of bandwidth. Okay. We know that for any amplifier, okay, if all the parameters are fixed, its gain and bandwidth, if you multiply them, we call it gain bandwidth product. GBP is a fixed quantity, or it's a constant. Okay. So, the gain bandwidth product, if you see, is a product of the voltage gain of the amplifier and the bandwidth of the amplifier, and as I mentioned that the product of them is a constant quantity. Okay. Means that if I say what I am telling, that voltage gain, okay, if you have studied amplifier, you might be aware about this factor. If you are not, then also it is fine. Okay. Voltage gain is into a bandwidth is a constant quantity. All right. Means that voltage gain can be reduced to obtain a wider bandwidth. Okay. Or bandwidth can be reduced or can be compromised to obtain higher gain without significantly changing the cost. This you can understand with the analogy a pipe. Okay. So, I have two pipes. Okay. One pipe is narrower and another is wider. Okay. Say water is flowing through both of them. All right. We can say that pressure in this case will be higher because the cross section is narrower. Okay. So, pressure is higher in this case, while the pressure that is coming out, or the water pressure that is coming out of this tap is smaller. Okay. So, smaller pressure at the output. Okay. So, through a pipe of narrower cross section, there will be huge amount of pressure generated at this cross section, and it will come out, with high pressure, while it will be a low pressure. Okay. Same thing is happening with a amplifier, since this multiplication or the product of gain and bandwidth is a constant quantity, means that if you are increasing the bandwidth, you have to compromise with the gain and vice versa. All right. However, similar to this, if you want high pressure as well as higher this opening or higher cross sectional, means that you may have to come up with altogether a new pipe which will have some other mechanism to enhance the pressure as well as to dispense larger quantity of water. Similarly, if you are not satisfied with compromised bandwidth or compromised gain, you have to come together altogether a new amplifier which will have a different gain as well as different bandwidth, and in that case the cost will be compromised. I mean, it will of course cost you heavily if you want both to be high, but then for that also it will be a constant quantity. Means that the gain and the product of gain and bandwidth will be again a constant quantity. Okay. So, if the gain bandwidth product itself increases, the cost of the amplifier will definitely increase. Okay, and this is one and only solution to increase this, the two compromise factors. Okay. The gain of the vertical amplifier determines the smallest signal amplitude that can be clearly displayed on the oscilloscope screen. Okay. And oscilloscope sensitivity is directly proportional to the vertical amplifier gain. We are not going mathematically, but you can understand that the sensitivity, which is represented as voltage per centimeter, okay, is directly proportional to the vertical amplifier gain. Okay. When you increase the gain, the sensitivity also increases. Okay. Higher sensitivity enables the oscilloscope to display and analyze even small amplitude signals. Therefore, the vertical amplifier plays a very crucial role in accurate signal observation on a CRT screen. Okay. Basic vertical amplifier of an oscilloscope consists of two major circuit blocks. One is this preamplifier, and then you have a mainframe amplifier. So, this whole configuration, including this preamplifier and a mainframe amplifier, is making a vertical amplifier. Okay. Mainframe amplifier is also known as a main vertical amplifier. Okay. And then you have a preamplifier over here. The preamplifier is a separate and can be interchangeable. I mean, you can simply plug it. Okay. And based on this plug-in, you can change these values. Okay. This can be easily plugged in and easily be plugged into the mainframe of the oscilloscope, which directly connects with the next stage, which is the mainframe amplifier. Okay. The active element in the first stage of the preamplifier is usually FET, which provide high input impedance of the oscilloscope. Okay. In the mainframe amplifier, the last stage is usually a push-pull amplifier, which provide voltage of equal amplitude but out of phase by say 180 degree to achieve a balanced deflection. Okay. After this vertical amplifier, you have a delay line. Okay. The use of this delay line is in the delaying the input signal slightly before it is being sent to the trigger circuit and then to the display. Okay. So, its major purpose is to ensure the waveform is displayed from the beginning, and it allows trigger circuit to stabilize before signal reaches the display. Okay. So, it is not only helping you with ensuring that the waveform is displayed from the initial part of it, but it also helps the trigger circuit to stabilize before the signal reaches the display. Okay. Without a delay line, initial part of the waveform may be lost and you may have only instantaneous result, which or maybe very kind of a few seconds signal, which is the result because you have lost the major part since there was no delay line available. Okay. Then I have a trigger circuit in this oscilloscope. The trigger circuit, this is a circuit system. This stabilizes the waveform on the screen. Without triggering, waveform will appear unstable and it will look like a moving waveform, while triggering will synchronize the horizontal sweep and the input signal. Okay. There are different type of triggering, but edge triggering is something which is very popular. In the edge triggering, what we do is there is a threshold set by the user. Okay. And when the signal reaches this threshold, then only triggering happens. But then there are other kind of triggering, like you have level triggering, video triggering and pulse triggering also available. Okay. So, depending on your requirement, you can use particular type of triggering circuit. Okay. Then we have a time-based generator, and time-based generator is a very crucial part of any analog oscilloscope. Okay. However, to understand the role of time-based generator, we have to understand the role of oscilloscope and different modes in the oscilloscope. Okay. So, we know that the oscilloscopes are used to display waveform that vary with time, and for accurate waveform production, the electron beam must move with a constant horizontal velocity. Okay. Beam velocity depends on the deflecting voltage, and therefore, the deflecting voltage must increase linearly with time. So, a voltage that increases linearly with time is called a ramp voltage. We have seen ramp voltage example in ADC as well. We have seen in fact a ramp generator also. Okay. So, I have a voltage and time, okay, on this screen, and This happens when voltage is increasing continuously. Okay. Now, if this voltage drops rapidly to 0, okay, and in place of going like this, okay, and then it start repeating like this, okay. So, please see that it is increasing slowly and then it is dropping at very fast rate. Similarly, it is repeating these values, okay. So, if this voltage drop rapidly to 0 and again repeat, the resulting pattern is known as sawtooth waveform. So, this is a typical example of a sawtooth waveform, okay. The role of time based generator is to generate this sawtooth waveform, okay. So, its purpose is to basically control the horizontal movement of the electron beam, and it also determine the time scale of the signal, okay. Now, consider a sawtooth waveform generated by a time based generator. Similarly, you can consider that there are n number of waves over here, okay. This part of it is known as sweep time and this is known as retrace time, okay. So, Ts is the sweep time and Tr is the retrace time, okay. During the sweep time, the beam moves from the left to right across the CRT screen, okay. The beam is reflected to the right by increasing amplitude of the ramp voltage. Now, during this retrace time, the beam returns quickly to the left side of the screen. The control grid is gated off, which blanks out the beam during the retrace time and prevents an undesirable retrace pattern from appearing on the screen, okay. After this time based generator has generated this sawtooth waveform, the role of horizontal amplifier begins, okay. The horizontal amplifier amplifies the signal from the time based generator, okay. So, its function is to drive the horizontal deflection plate of CRT and also to control horizontal movement of the beam, okay. So, this produces the time axis of the output. Before understanding the function of this horizontal amplifier, we have to again understand that the oscilloscope can operate in two modes. We have discussed this in initial of this lecture. We have seen that there are two modes. One is the normal mode, sometimes also known as time based mode or YT mode, and then we have a XY mode of this oscilloscope, okay. The horizontal amplifier in an oscilloscope is a crucial block that controls how the electron beam moves along the x-axis or the horizontal direction of the screen, okay. Its role changes depending on how the oscilloscope is being used. It is being used in the normal mode or it is being used in the XY mode, okay. When it is operating in the normal or time based mode, the oscilloscope displays voltage versus time, okay. The vertical axis shows the input signal amplitude like this, okay. Say this is the voltage and x-axis represent the time, right. The sweep generator or the time based generator produces a sawtooth waveform and the waveform increases linearly with time and moves the beam from left to right. The role of horizontal amplifier here is to amplify this sawtooth signal and also to provide sufficient voltage to drive the horizontal deflection plates. We know that the sweep generator's output is usually of very low level and that is why amplification is required, okay. Deflection plates also require a higher voltage for proper beam movement and therefore, the amplification becomes very crucial. The amplification here ensures proper scaling of time axis, adequate linearity of the sweep and clear and stable waveform display, particularly at the horizontal or in the x-axis, okay. When you talk about operation of this horizontal amplifier, when this oscilloscope is working in the XY mode, the oscilloscope actually displaying one signal versus another. So, you have here also voltage and here also voltage and there is basically no time sweep, okay. Instead, what you have is vertical input is also displaying certain voltage and horizontal input is also being displayed as a voltage, okay. Horizontal amplifier amplifies the external signal applied to the horizontal input terminal and sent directly it to the horizontal deflection plates for their deflection, okay. So, when the oscilloscope is being used in its ordinary mode of operation, the gain and bandwidth requirement for the horizontal amplifier are not as stringent as that of the vertical amplifier, and it can be, the requirement in this case is less demanding, right. Similar to the vertical amplifier as well, you can see that horizontal amplifier final stage is also a push-pull stage, okay, means that you have that 180 shift at the output, okay. Then after this deflection at this particular front, you have CRT or the display, depending on what display you are using. The conventional, as I have mentioned, use a CRT, okay. So working principle of CRT is very simple. You have an electron gun which emits an electron beam strikes a phosphor screen, and phosphor glows to produce a waveform. Since this is say a spot that is being created by very sharp electron beam, it looks a kind of glowing spot on the screen, okay. So a cathode ray oscilloscope, as the name suggests, consists of a cathode ray tube, which is the heart of this particular system, and there are some additional circuitry to operate this CRT, okay. The main part of a CRT is a electron gun assembly, a deflection plate assembly, fluorescent screen, an envelope to accommodate all of them, and a base through which connections are made to various parts. This is a typical CRT. You can see that this is the display I was talking about, where this luminous spot is getting created by this electron beam, which is getting generated, if it is say heater based generation, or it can be a field emission based generation, okay. So this is getting generated, and then you have a different lens system to focus this. Similar to the optical rays, say photons, which can be deflected by a lens system or a mirror system, okay. These rays are actually, this electron beam cannot be deflected by a simple lens and mirror system. For them you need a electromagnetic lens system, okay. So they are deflected using various electromagnetic system, and then you have anodes which actually attract this electron beam and accelerate them, and you have vertical deflection plate as well as you have horizontal deflection plate. So two pair of plates are there for their deflection, okay, and these are various components that we have already seen: vertical amplifier, delay line, trigger circuit, time based generators, horizontal amplifier, okay. So everything is present over here, and this electron get deflected. I mean, these horizontal deflection plates are getting deflected by this output from this amplifier. Similarly, this vertical is getting fed by this vertical amplifier using a delay line, and accordingly you have independent movement of this electron beam on this or this luminous spot basically on this phosphor screen, okay. So the electron gun assembly produces a sharp focused beam of electrons, in this case of CRT, which are accelerated to high velocity using various means of the arrangement of these anodes, okay. This focused beam of electron strike the fluorescent screen with sufficient energy to glow it, okay, and you have a luminous spot on the screen, okay. After leaving the electron gun, the electron beam passes through two pairs of electrostatic deflection plate, which we have seen, okay. Voltage applied to these plates deflect the beam. Voltage applied to one pair of plates move the beam vertically up and down, and the voltage applied to other pair of plate moves the beam horizontal from one side to other, okay. By this you are having independent control, or the beam can actually move independently on the screen, okay. So these two movements, horizontal and vertical, are independent of each other, and therefore the beam can be positioned anywhere on the screen by using X and Y deflections, okay. So all the working part that we have seen for a CRT are enclosed in a evacuated glass envelope, so that the emitted electrons are able to move freely from one end of the tube to other end, and that's how a CRT basically works. The modern systems in analog oscilloscopes also have LCD and other digital displays, okay. Now this is about the analog oscilloscopes. We also have digital storage oscilloscopes or digital oscilloscopes, okay. A DSO is an advanced electronic instrument used to capture, store, analyze and display electronic signals in digital form. Unlike analog oscilloscopes, a DSO converts analog signal into digital data allowing long-term storage, processing and further analysis. Okay. This is a typical block diagram of a DSO where you have input signal which is fed into a input attenuator or a amplifier depending on what is required. Then the signal is fed to a sample to hold circuit because we have to feed it into a ADC for digitizing them, and then you have a memory which can store the data and a microprocessor which can process this data, and then finally you have a display unit. Okay. The basic working principle of this DSO is also very similar to what we have seen. Okay. We have your input signal acquisition. The electrical signal is applied through a probe that we have seen in the analog oscilloscopes also, okay, which is then fed into the signal conditioning unit where the signal is amplified or attenuated depending on what is required to a suitable level. Then the output of that has to be fed into a ADC, but we have seen that before we fed anything to ADC, particularly high frequency or high bandwidth data, we have to use a sample and hold circuit. Usually DSOs are more important or more crucial for high frequency signals. Therefore, a sample and hold circuit is essential to this DSOs. Okay. The analog signal is sampled and converted into digital form in this ADC, and then you have memory storage where this digital data is stored, and then it can be displayed or it can be analyzed depending on what you want with the data. So, if I have to summarize the key features of this DSO, I can say that this DSO has a better storage capability than what we have seen in the analog storage or analog oscilloscope, which has a limited storage capability. So, it can store waveforms for longer duration and you can recall them at any time. So, later analysis and comparison of all kind of waveforms is possible. Okay. This also allow you to digital process the data. So, all kind of mathematical operations like FFT, filtering, averaging, all these things can be done it at later stage. You do not have to do on the same time. Okay. DSO have higher accuracy, so it reduces noise and distortion through digital processing. Okay. The DSO have triggering capabilities, so they capture specific events like you can capture edges, pulses and glitches during the triggering. Okay. Data transfer is possible through different connectors like USB, LAN or other wireless networks. Okay. So, these are basically the strength of DSO. They can store and recall waveform, enable advanced signal analysis. They are even compact and portable, although they are also kind of portable, but DSO have an edge in portability if you compare it with the analog oscilloscopes. Okay. Data sharing and documentation with DSO is also very simple, and better visualization of transient signals are possible in DSO. However, they also have various limitations, like they are limited by their sampling rate, because of which it may miss very fast signal changes. Okay, means that aliasing can happen here. Okay, they have finite memory depth, which restricts recording duration of the data. Okay. Quantization error can occur in this DSO, which may occur due to digital conversion, which is basically the resolution limit of DSO. Okay. It suffers from bandwidth limitation and thus cannot capture very high frequency signal accurately. Okay. They have higher cost and complexity because you are calling or you are putting a digital processor. Okay. So, of course, the cost will go high. Okay. It suffers from real-time display limitations and may not show very fast transient events perfectly. All right. So, these are some of the demerits of DSOs, and mostly in the laboratory conditions we still rely upon the analog storage oscilloscope or analog oscilloscopes. Okay. DSOs are special oscilloscopes, particularly still it has limited use in academia, and in all the laboratories we are still using the analog oscilloscopes, but then DSO have their own advantages, particularly when you talk about storing the data and all. Okay. Now, we have understood the oscilloscopes. Okay. In the next class, maybe we can discuss the wave generators that are useful in the instrumentation, and we'll also see signal analyzers. Okay. So, two important topics that we are going to cover in the next lecture are the waveform generators or signal generators and signal analyzers. Thank you.